Howdy, everybody. Hope you're having an amazing day, evening, morning, wherever you may be. Hope it's, or whatever time it is as well. Hope things are going well for you. I just wanted to, before we get started again, to say thank you. Always appreciate the comments and feedback. It's fun to interact and to learn more. The last video, for example, a lot of people mentioned that I hadn't brought up grapheme clusters. I usually just call them graphenes. But the idea that sometimes some characters are made up by multiple UTF-8 characters. I stuck to the Rust library in that last video, and that's why I didn't talk about it. But it is a good point to bring up. So it's always fun to interact with you and get your information or get your knowledge and stuff like that out there, so we can all grow and learn together. So thank you very much. It's always fun to interact with you. Now, the next several videos, what are we going to do? Well, I want to go back to Intcode, and this all started, ironically, not in Intcode. I was doing the exorcism exercises. I don't know if you've seen those before, gone to exorcism.io before. It's like a place where you can solve puzzles. And they're usually not too hard puzzles, and it's mostly meant for you to help learn a new language and solve puzzles in those languages so you feel more confident in that language. They're doing a program called 48 in 24, which is like 48 new languages. Can you do these puzzles in 48 languages over the year 2024? So they're going to give us puzzles and you solve them in different languages. And some of them are languages I've never used before. One of them was MIPS, which is a little bit like, I don't know. I don't know a lot of details about MIPS. If you know more about it, I'd love to hear about it. But it looks like it's a little bit like assembly language, where you're, using instructions that are like very, that are much closer to the CPU and the memory than like you would use in something like C or Rust or Go, for example, PHP, whatever. And it reminded me of my I don't know, my old college days where you actually learned at kind of a high level how a CPU works. How does it take your program and process it in memory? And as I was looking around for like, what would be some good ways to like discuss that in a video or whatever, or talk about how that works, I found out that Intcode in the year 2019, several of the days you actually build an Intcode computer, which is just a virtual machine that runs this Intcode program that you set up. And apparently it was really fun for a lot of people to like implement it. And so my hope is that we'll go through it and we'll learn a lot. Again, the idea is it will be a high level introduction to how your computer works, because you'll be like creating that computer in a programming language. And feel free to do it in whatever language. I'm going to try and do it in Rust, but I'd be happy to look at your code, or be interested to look at your code if you're doing it in Python, C, whatever. MIPS, probably a little harder, but I'd love to see what everyone's doing. So anyway, that's the goal for the next several videos is, can we go through these Intcode days in 2019 and create an actual virtual machine for this Intcode computer, so that we can run this Intcode, and then hopefully from that we will learn kind of at a high level how our computer works, right? And so with that, I think we should just get started and kind of learn along the way, right? As I was reading through day 2 and I started with the next one, day 5, it does a really good job of kind of explaining how computers work, from the sense that, hey, you're trying to solve this puzzle, here's what I want you to do. So here we go. This is day 2, and what's happening is you are trying to find Santa in the solar system or space or whatever. I don't remember exactly where. Maybe the galaxy. Anyway, he was off delivering present somewhere else and is stuck, and your job is to go find him and bring him back to Earth so he can deliver Christmas here on Earth. And as you're up, the computer breaks down. And so your job is to rebuild the computer, is essentially what it's saying. One of the things I really liked is it said that the computer's magic smoke seemed to have escaped. Fortunately, I've not seen a lot of magic smoke in my days, but I do have a really funny story. When I was in high school, I was learning about computers, and my teacher actually put I'm almost positive it was the CPU. He put the CPU in the wrong direction and kind of forced it in. If you've ever made your own computer, they often don't fit very well when they're in the wrong direction. But he started it up, and a burst of smoke came out of the CPU. It was a funny moment, and he was just all like, well, that's not supposed to happen. And he said, the magic smoke is not a good sign, and that's where I first learned about the word magic smoke. So anyway, the computer is broken. Your job is to build a new computer that runs Intcode programs, right? So right now we're doing the gravity assist one, so we can help use it to like find our way to Santa and stuff like that. And apparently in future days it's going to get harder, but they're just going to start us up with a very simple computer. And what they say is you need to create a computer that will run these Intcode programs. And the Intcode programs are just lists of integers. I guess that's the Intcode where it comes from, right? You're going to get a bunch of integers as your input, and you're going to use those integers as your program and do some processing. And what it tells you is that each program has an how do I say this? Each program starts at the beginning, and the very first item is an opcode, and that opcode tells you what you should be doing. So in normal computer architecture, you can think about this as like the operation you want to run, or the function you want to call, or something like that, right? At a bare level, it's all. I mean, the int code is kind of interesting because on your CPU, it's all just ones and zeros, right? And they aren't necessarily integers, but it's all just ones and zeros, and they're just going through the computer. But those ones and zeros have instructions, right? You have like an instruction that you want to run on your computer, and that usually is an opcode, right? And they'll say like, add is this, and in our case, add is 1, and multiply is 2. That's what this thing is telling you. It's like, so you start at position 0, and you're going to get an opcode, right? You're starting at position 0, you're going to get an opcode, and if it's 1, that means add. If it's 2, that means multiply. And then they give you a third one, which is 99, and that means halt the program. Stop what you're doing, right? But in between all of that, each of the opcodes have parameters, right? They have like values that you want to do that with. For example, if you're going to add, you obviously need to know what 2 values am I adding, and where am I putting the result of that in memory? Like, where does the result go, right? So the add operation actually has 3 parameters. It's the 2 values you want to add, and where do you want to put it, right? So you can think about it as the left, right of the add, and then the destination that you want to put that result. So if you're adding 1 plus 1, you get 2, but where do you put it in memory? The destination will tell you, right? Multiply is the same thing. You're going to have 2 numbers. You're going to multiply 2 values, and then you have to put that somewhere. So it's going to tell you the memory location that you want to put it. And again, this is actually pretty close to how computers run, right? Is like you give the computer an instruction, and that instruction has, the parameters that you need to do it, and where you want to put it. Maybe I can actually find MIPS commands. So you can see, I think this is the one I found. When I was solving the exorcism one in MIPS, you need to like know these things, right? And so you can see here is if you want to add, you have to give it 3 values. In MIPS's case, it's destination, left, and right. And what it translates to is add 2 and 3 together, and then put that value in position 1, or in the memory location 1, right? Now, it's usually the case that, at least for your computer programs, you will, oops, what did I do here? You will not be, in real computers, you often don't, you have like your program you run and then the memory that is attached to it, and you don't like let the two interact, because there's security considerations there. But for our case, it's saying treat the whole int program as the program, but also the memory. And so you're going to update the values in there and change them. Was that confusing? That was a little confusing. The way to think about it is the program you're going to get, which is this, is going to be the memory. It's going to be everything, and it's going to tell you what to do and where to do it. And you can just treat this as kind of like a vector of memory, and you're going to take the int opcode, figure out what you need to do with the parameters next to it, do that, and then put that thing back into the memory. Okay. So it gives you some examples, and it splits them up here. Notice that the add and multiply have 3 parameters. So it actually takes this single line and breaks it up for you like this. And that's what it looks like, right? I thought it would make sense, though, to kind of do this in here. It is a spreadsheet, but hopefully it'll give you an idea of how it works and we can step through it. And I've done the same thing. I've kind of broken it up. I did look a little bit at the next day for this, and this is not always going to be the case, but at least for today, the add and multiply always have 3 parameters, right? And so, but they're basically saying, here's what you need to do for each of those parameters, okay? So I thought it would be fun just to step through it and see how it works. One thing to note before we get into it, though, is when it tells you to do something, what it's actually, when it gives you a parameter, that's the memory location for the value, right? So when you see 1, 9, 10, 3, this is add 9 and 10. It's not saying add the values 9 and 10. It's saying add the values at the memory locations 9 and 10, right? So 4, 8, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It's saying add 30 and 40 and place it in the third one, right? So you can see that's what it's doing right here, right? Add 30 and 40 and place it right here. Replace that 3. Okay, so that's just a key thing to think about as we're stepping through it. So let's actually step through it. We know 1 is add, and our instruction pointer is currently at 0. And so what do? We look at memory location 9 and 10 and add those two and put it in the memory location 3, right? So this is memory location 3, and this is 9 and 10. So we're going to do 30 plus 40 is equal to 70, and we're going to put that value in 3. So 0, 1, 2, 3. So we're going to replace this 3 now with 70, right? Now what do? Well, how does a program run? How does like your computer know what to do next? It keeps an instruction pointer. It's also called a program counter. And it's like, the way to think about it is, what is the next line of code that you want to run, or what is the next instruction you want to run, I guess I should say. So we were at 0, which was right here, but we've now used all of these. So we're going to move to this one. So our next instruction is 4, right? So we'll update that, and now the CPU will know, hey, we're on instruction 4, and we want to process it right here. So let's do that. 2 is multiply, and so it says multiply 3 by 11 and put it in position 0, right? Put it in memory location 0. And remember, it's not 3 and 11, it's the memory of 3 and the memory of 11, right? So we have 8, 9, 10, 11. So 50 times 70 is 3,500. So it's saying 70 times 50, put that in the 0th memory location, which is right here, right? So we're going to put that in there. 3,500. We did it. Now we're going to update our pointer, our instruction pointer, right? We were at 4. So we're going to, and we use these, all of these right here. So we're now at 8. And this, and so what is the next instruction? It is 99, which is halt, right? The program tells you somewhere in here, it says, hey, when you're done, or the program ends when it hits 99. Yeah, the program is finished and should immediately halt. So that's how this program runs. And so now this program is done. And then this is the final memory. This is what the memory looks like after it is done. So what it's telling you to do is run, at least day 1 is telling you to run your program. You're going to get all these bits and you're going to just do that iteratively, right? We only had 3 instructions, but you're going to get a bunch more and your job is to process them all, right? You're going to go through the whole process, and once you're done, you're going to output the first memory location. So the memory location 0 is the way to think about it. What it tells you too is it says set the 2 values to set the initial positions to 12 and 2. And you can think about that as just like the initializing your program to those 2 values to run, right? The way to think about this is we've created some program that's going to update this value right here. This is a very small one. We've created a program that's going to add these 2 values and then multiply it by this value and put it in here, right? So if you were in like Python or whatever, you may say A is equal to B plus C. What would it look like? B plus C times D. That's what this program is doing. And A would be this position right here, right? That's you can think about that's what this program does. And this is what your CPU does, again, at like a very high level. When you say that, it does this work in your computer. What they're telling you is, what I want you to do is, now that you have that program, I want you to replace position 1 with 12 and position 2 with 2 in your program. So this, instead of being 9 and 10, this will be 12 and 2. And then I want you to rerun the program and see what it outputs here, right? So this is the initial program, and you're going to update these values here, and then you're going to do that process, right? So 8, 9, 10, 11. We don't have a 12. Let's say we did have a 12 and it was, I don't know, whatever, 40. But the idea is you would take this and run this program and process it that way, right? So I'm going to reset this so we're back to our original value. But hopefully that gives you an idea of what they're trying to get you to do, right? Is you're going to have some amount of memory. You're going to process it in a linear fashion, pulling instructions out of it, which includes an opcode and all of its parameters. And you're just going to slowly go through all the memory, slowly updating the instruction pointer until you get to a halt, right? So that was a lot of discussion, basically just to say, we're going to build a mini computer, we're going to have memory, we're going to go through that memory and look for and iterate over the instructions, and eventually we will halt. And then when we're done, at least for day 1 or day 2 in this case, the first instance of this program, the output is going to be this value, right? So let's see how that looks in code. Let's just focus on part 1 for now. You can see here's me doing it. Basically, I get my input and I'm going to create a new computer with that program, right? Where my input is the program. And I'm going to update my 2 values, right? I'm going to set my memory location 1 to 12, and I'm going to set my memory location 2 to 2, right? And then I'm just going to run the program. I noticed in one of the comments someone mentioned the halting problem. it tells you a lot that we just assume that the program finishes, but that is kind of a funny thought is hopefully this run finishes, right? You could potentially get yourself in a loop that lasts forever and never actually finish. Um, but we're just going to assume that it does, right? So we're going to, again, we'll create a new computer with that program, update our inputs or our values, and then run that until it's finished. And then it says the answer is at computer 0, the 0th position, right? So what is the question though then is, what does that computer do? Well, I kind of wanted to break it up in a couple ways. Obviously, we have a new computer, but we also have a list of instructions, right? And I thought this would be helpful to do an enumeration, right? Because it it seems like a very natural thing to do with a list of instructions is to have like an enumeration of them and what parameters they expect, right? So we know add requires 3 values, multiply requires 3 values as well, and then halt requires none of them, right? So what we can do is basically when we're pulling out value or when we're getting the next instruction, we can use the enumeration to like get that stuff we can create an enumeration, one of these values, I guess I should say. And then when we're running the program, we can handle those instructions based on each of those enumerations. Okay, and then what does our computer look like? Well, it's just some memory and the instruction pointer, right? Again, we have a very basic computer at this point. It will get more complicated, but you can think about when we were walking through the example, all we really had was an instruction pointer and a memory location, right? Or I guess I should say a bunch of memory, right? So I just use the memory as a vector. That seems easy enough because we'll be iterating through it. We want to index through it pretty easily, and then we'll have an instruction pointer which tracks where we are. So when someone says, hey, give me the next instruction, we know what point we are in memory to do that processing, right? I did some of these helper functions, so it's easy to index into the memory. So that's what these two impls are. They allow you to like modify the memory or get the memory location just by using, for example, you can see here I say computer 1 equals 12. That simplifies that process, right? As opposed to having to dig into the memory to find it, for example. But then here's our computer, right? So how do we create a new computer with our program? We basically just split by commas. We turn them into integers, which are I size, right? Or you could use I32, I64, whatever. We just collect them into a vector, and that becomes our memory. And then we initialize the instruction pointer at 0, right? It says we're starting at the 0th point in time. So what does our run look like when we call run? Well, we have to have some function called next instruction, like what is the next instruction? We'll worry about that in a minute. But what do we do? Well, if we just enumerate over we just match over that instruction, right? So we say, if it's an add, we're going to add the 2 values and put it in the given destination, right? And notice this is the memory locations again, right? So we're saying take the memory locations at left and right, add them together, and put them in the destination. Multiplies the same. Take the memory locations, or the values at the memory locations left and right. Sorry if I'm saying that wrong. It's the values at those memory locations, and multiply them together and put them in the memory location dest, right? And then finally, if it's halt, we're done, we can break, right? I do put this in a while loop because we can call while let some next instruction. I don't know if it would ever fail because, again, they say if you ever get to 99, you're done. But I have a little check in the next instruction that basically says, hey, if I would go over memory, I'm just going to return none instead, and that's another signal that you're done processing, right? So it may never actually happen in the code, and you could potentially just loop forever, but this felt like a clean way to do it, right? So when you're running the program, you're just saying, hey, what's the next instruction? And then perform that instruction and go on until you halt and break, right? So what does that next instruction look like? Well, here's that check that I was talking to you about, right? If If the instruction pointer is greater than the memory length or equal to it, we know we've gone too far, and so we're done. Otherwise, we just figure out what the next instruction is, right? So we say, hey, go get the value at the current instruction pointer. So like right here, it's saying get this value 1 and compare it and just do a match over it, right? So we know if it's 1, we're going to do an add. We know if it's 2, we're going to multiply. We know if it's 99, we're going to halt, right? So what do? We obviously we need to get the parameters for those, right? So if we're at memory location 0 and our instruction is 1, we know we need to add these two and put them there. So we need to get these 3 values, right? Well, what does that look like? Again, we basically just say, hey, get the next memory location for the first parameter, and then the one after that for the next, and the one after that for the next as well, right? So I think I could have actually done this. It's funny that I put these like this, right? I could do this, I think. Rage. I think that's still right. But because I have that, again, I'm doing that index mute. But again, what are we doing? Well, I need those additional memory locations, right? I need to know what these values are. And so if this is our current position, this is our current position plus 1, our current position plus 2, our current position plus 3, right? And so that's basically what I need to do, is get those values. In Rust, we have to cast them as a usize at some point, because we want to be able to, we know their memory locations, and so we want to be able to index into the memory, and you have to use a usize for that in Rust, so that's why we do that. But that's it. Now we've created our instruction, and then we update our instruction pointer and return that value. And that's the gist of it, right? At least for day 2. I'm positive it will get more complicated, but for your initial implementation, at least for me, that's all it took, right? Is I added some stuff here that you potentially don't have to do, right? I created this enum. Most of that's just because I'm figuring in following days it's going to get substantially more complex, and so having this enumeration will help. I created the computer in its own thing because, again, it's having the memory and the instruction pointer kind of in the same place is good. If there's inputs and outputs, knowing, or as we start doing like IO or increase, or maybe like the options, for example, in a real computer, like in the MIPS thing, I don't think I have that up anymore. You can like jump to different locations in memory based on commands. You can think about those as like if blocks, like if this is true, go here. That would update your instruction pointer. So having this all in one place felt good, right? We'll see, though. I may be doing all this and it may not be useful, or it may be so complex we have to break it up even more. But this felt like a good start to me, right? Is let's create a computer that will run some instructions. Let's have like a run function or a run method that will go through all the instructions and process them until it halts. And then let's have this little next instruction thing that does the job of like figuring out what the next instruction is to run based on the integers or the values you're given, right? So there you go. That's day 2, and I guess I can run it so you can see it. So you can see it finish. These were my answers. Not too tough, but again, like what I really want to say is, this is not too far away from how your computer actually works, right? These things are, if you go searching Wikipedia, or you get a book on this, or you look at how this design happens, this is very much similar to how your program runs. Again, it's much more complex, right? Because your CPU's speeding things up, doing things in parallel, context switching. It's doing all that crazy stuff, but it's got a bunch of memory. Your program is going to build, and it's going to load that program into memory, and it's just going to start processing it one instruction at a time. going through all of those instructions, doing what you asked it to do until you tell it to run, right? We've done a very simple program today where we just add and multiply and then get the value of that add and multiply. But it worked, right? And that's the beginning. That's like the ground base that you need, right? Is can you find instructions? Can you process them? And then I'm sure complexity will come after that, right? Really quick, if you want to see how part two is done, basically what part two says is, okay, after you've run that first program and you've figured out what's wrong with it, now you need to figure out, now can you set up the program? Can you figure out what two values you put here, I guess I should say, so that you get this value? And for me, it was easy enough just to iterate through. It says it's two numbers between 0 and 99. Just run the program until you get that, and then tell me, like, do some math to figure out what the output is or what the answer is. So it wasn't much more hard. Once you figured out how to do part one, for me, it was just 2 for loops. The n is small here. The size is really small. So I could just create my computer, run it with those two values until I got that answer. So I haven't looked at anyone else's code, but it'd be interesting to see. I know some people have already done it, and so they have like their final program. I'll really be interested to see how those look at the end of it. But again, I'm very interested in your code. I have a gist posted. I'm going to update the gist with my answer, but I'd love to see what your solutions are, how you run it. And as we go through the days, we'll compare and contrast, especially as things change, right? This is the thing that I think is cool about this. We're starting off at the base, but it's going to grow. It's going to get bigger. It's going to be more complex, but it will do amazing things. And it will cause us to do some refactoring, which is, I mean, that's pretty common, right? If you think of any real world scenario, start small, get stuff done, and then refactor as you need more features and stuff like that, right? So there you have it. That's day 2 for Advent of Code 2019. I'm really excited to see what comes next. Again, I love the idea of kind of implementing this computer. I think it's a cool puzzle that will help you learn and understand kind of how a program works. And it will help, it'll help kind of reinforce what's happening at that computer level. Even if it's just in a fun, very abstract way, right? So there you go. The next video I think is for day 5. So I'll post a message about that, and love to see your feedback about that. But otherwise, hope you all have an amazing day, night, weekend, whatever, whenever you may be watching this, that things are going well. And we'll talk to you next time.